Biopots, potential use for greenhouse production and landscape planting. Research projects typically start with the problem and work towards finding a solution to that problem. Plastic pots have become the industry standard because of their durability and their ability to be made into many sizes, shapes, and colors. Plastic pots are also easily stacked and stored and can withstand greenhouse automation, transportation, and marketing. The downside to the plastic pot is the issue of proper disposal. Unfortunately, the horticulture industry contributes a large part to the overall waste stream in the U.S. For some greenhouses, reusing is an option, but for many, the cost of sterilizing just isn't feasible. Recycling is another option. However, recycling of agricultural products is often complicated by contamination, dirt residue, grease, pesticide and fertilizer residue, and UV light degradation. Since recycling options for containers is limited and reuse is not always feasible, the industry must move in a different direction to reduce plastic use. One possible solution is the use of biopots. Biopots can be either plantable or compostable. Plantable biopots are designed to be left intact on the root ball and allow the roots to grow through the container walls. Compostable biopots are designed to be removed before planting. This research is funded by a USDA SCRI, which stands for Specialty Crops Research Initiative. Along with West Virginia University, there are many other universities involved, including the University of Arkansas, University of Illinois, Mississippi State, Texas A&M, Michigan State, Rutgers, University of Tennessee, and the University of Kentucky. Here at WVU, we are involved in 3 tasks, involving the potential use of biopots in a greenhouse, nursery, and landscape setting. I'd like to start with showing you my research study grown at the WVU greenhouse on the Evansdale campus. For this experiment, I have a short-term 6-week trial of sun patience and a 12-week trial of lavender grown in 10 different pot types. Each trial is grown on a different table. On each table, there are 180 plants with 10 different pot types. Surrounding the pots are a guard row of impatiens. On each table, there are 3 trays of each pot type, randomly arranged. Within each tray, there are 6 pots. Each pot is assigned a unique number and letter corresponding to its placement within the tray and its placement on the table. Although the experiment has ended for this season, the guard row is still left on the table. I'd like to take a moment and introduce you to the biopots used in this study. Shown in alphabetical order, we have the core pot made of coconut, the control plastic pot, cow pot, fertile pot, jiffy pot, the net rice hull pot, OP47, solid rice hull, soil wrap, and a straw pot. Temperature and light are monitored for the experiment using a PAR sensor, which is connected to a watchdog data logger. Here you can see the data logger displaying the current temperature and the amount of light that is being received at that moment. One of the measurements taken for this experiment was watering frequency per pot type. Plants were monitored on a daily basis, and each tray was watered if it fell below a certain moisture content. The moisture content of a pot was determined using a Field Scout sensor and probe. Here you can see the moisture probe being inserted into the pot. Lavender was watered if the moisture content fell below 30%, and patience were watered if the moisture content fell below 40%. Another measurement taken biweekly using a TechPro 2 meter was a EC and pH reading. EC, or electrical conductivity, is a measure of soil salinity. Plant fertilizers are composed of a mix of salts that are electrically conducting. Therefore, EC can be used as a measure of fertilizer concentration. For this experiment, the pour-through method was used. 80 ml of water was poured into the plant in question and allowed to drain for 5 minutes. The leachate was then collected and poured into the EC/pH meter. When using a meter of this type, it is always important to triple rinse. This means you fill the meter with the leachate you are testing, then dump and refill it 3 times. Once triple rinsing is complete, we select what we are measuring for. As you can see, I first selected pH. pH is defined as the concentration of hydrogen atoms. It is measured on a scale of 0 to 14, with 0 being the most acidic and 14 being the most basic. pH is important because it affects nutrient availability in plants. With just a press of a button, I'm able to obtain the EC reading of our leachate. Plants vary in their sensitivity to salts, but in general, 3000 is considered a high reading. In addition to plant growth parameters, we are also interested in how well the biopots withstand greenhouse conditions. The plants in pots shown here have just been removed from the 12-week greenhouse trial. If you look closely, you can see varying degrees of degradation among the pots. Also, be sure to note the similarities in growth. And now I'd like to give you a closer look at what some of these biopots look like after 12 weeks in the greenhouse. Shown here is a cow pot made of composted weed seed-free manure. As you can see, there's not much of the pot left after 12 weeks, and the roots are fully able to penetrate what's left of the container walls. The fertile pot is another biopot that is plantable just like the cow pot, although it lacks the special aroma that comes with the cow pot. Fertile pots are composed primarily of spruce fibers. As you can see, this pot holds up pretty well in the 12-week experiment, but we do see a bit of algae growth and root penetration. Next, straw pots. Straw pots are produced from natural ingredients including straw, coconut fibers, and a natural latex adhesive. The company claims that the pots will degrade within 3 to 6 months in the landscape. Overall, the pots held up well in our 12-week study aside from some minimal fraying. This is the Jiffy pot, composed mostly of peat. This is a plantable pot along with the straw pot just shown. Again, we see some algae growth, but overall the pot holds up well in greenhouse production. Next, we have the solid rice hull pot, a compostable pot made by Ball. They are made from rice hull fibers, a sustainable plant byproduct. The pots look and feel much like plastic, but are somewhat fragile. Core pots are a plantable pot made from the fiber of coconut husks. A neat thing about this pot, they have shown resistance to bacterial and fungal growth. The OP47, also known as wheat pots, are made from biopolymers and look and feel very similar to plastic pots, but are compostable in appropriate conditions. The control pot used in this study was a traditional 4-inch plastic pot. The netted rice hull pot is the plantable rice hull version made by Summit Plastics. The pot has holes on the bottom and slits on the side to promote root penetration. As you can see, at the end of the 12-week experiment, the pot is still very intact, but the fibers have begun to break down and the pot has become fragile. And last, but certainly not least, is the soil wrap. This bottomless wraparound sleeve consists of morel, a material made from biopolymers produced by microbes. Soil wraps are easy to pack and store. According to Ball, 2.5 times more soil wrap containers can fit on a pallet compared to a plastic pot of the same size. As you can see, the soil wrap breaks down easily over the 12-week period. At the conclusion of the experiment, the pots are packed into bags and sent to the University of Arkansas. Here, punch tests are performed on the pots to determine strength. One of the last growth parameter measurements taken on the plant is leaf area, which can be determined using a leaf area meter like the one shown. In order to obtain a measurement, the leaf is placed on the transparent belt and travels under a fluorescent light tube. If we remove the back cover, you can see the series of 3 mirrors that reflect the leaf projection. The third mirror reflects the leaf image to a linear array solid-state camera. The camera senses the object width and length. The main circuit board then calculates the total area. As the sample passes under the light, the leaf area is shown on the LED display. As you can imagine, leaf area is a very tedious measurement to take. With 360 plants in the experiment, it takes many hours and lots of friends. Now, in much less detail, I'd like to show you my landscape and nursery biopot experiments. Both experiments are at the WVU Agronomy Farm. The landscape experiments use the same 4-inch plantable pots that I've just shown you in the greenhouse experiment. The landscape experiment has 3 trials: a high water input sun patience trial, a medium input cleome trial, and a low input lantana trial. The pot types are randomly planted in rows of 8. The plants are grown out in the WVU greenhouse for 6 weeks in biopots and then planted in the landscape after danger of frost. They will remain in the ground for 12 to 16 weeks. Throughout the season, plant growth measurements such as height and width, as well as quality ratings, are taken on each individual plant. At the end of the season, the plants are harvested and measured for both fresh and dry weight. And then the real work begins. Once the plants have been harvested, each pot is retrieved from the ground and individually photographed. All 240 pots. So, if you're still with me, I have one more thing to show you, and that's my nursery experiment. The nursery experiment tests 4 different pot types, replicated 3 times among 12 blocks. The pots are of 1 gallon size. Shown here is a first-generation keratin pot. We also have a cord fiber pot, and a traditional black plastic pot serves as our control. Also, a root pouch pot. Research pots are arranged in 3 rows of 5 and surrounded by an outer guard row. This experiment is designed to use an overhead irrigation system. This particular irrigation system uses probes to measure the amount of water used daily by the pots. The water content of the pots is relayed back to the central computer. The computer then calculates the amount of water lost and how long the irrigation system needs to run in order to reapply the needed amount. I have some preliminary results to share with you from the greenhouse study. Our data was analyzed using a one-way ANOVA, and means were compared using the Tukey-Kramer method. With few exceptions, biopots perform similar in growth parameters compared to plastic pots. In punch tests, plastic pots outperformed all biopots except coir and rice hull. In conclusion, it seems that biopots perform similar in greenhouse production to a traditional plastic pot. We feel that ease of handling before and after production will likely have a greater influence on pot choice. Certainly, I would not be able to do this work alone. Special thanks this year to Whitney Garten, Bev Schell, Millie Mullins, Alicia Schiffer, and my graduate mentor, Dr. Sven Verlinden. This video can be found on YouTube, or you can search the WVU Organic Farm Field Day Biopot presentation. Once again, my name is Renee Conneway, and I welcome any questions you may have. Thank you for attending this workshop and for attending the 2012 Organic Farm Field Day. Hope you enjoy the rest of your day.